This is section 1.7, solving compound inequalities. So in the last lesson we talked about solving regular inequalities, and now we're going to talk about compound inequalities. So a compound inequality is an inequality formed by joining two inequalities with the word and or the word or. So you're going to solve it just like regular, but now you're just going to have two inequalities to solve. So for and inequalities, there are two ways you might see them. You might see them as one, it looks like one inequality, but it has two signs, two inequality signs. They should be facing the same direction. The other way that they would write this, and these two are exactly the same, is writing it using the word and. So when we have an and inequality, we're looking to see where the two inequalities overlap on the number line. So the solutions for that compound inequality are all the numbers that are true for both. So the graph usually is going to look like a shaded portion on a number line. So that would look like, so if it was between these two numbers, let's say we have open circles, it's going to look like this, anything in between these two. If for some reason you get an inequality that when you graph it, it looks like this, and it's an and inequality, notice that they don't overlap. If they don't overlap, then there is no possible way you can find a number that works for both inequalities, so this would be a no solution. So let's try it out. Actually, we're going to go to or inequalities quick. So an or inequality, there's only one way to write it. You have the word or. Solutions are going to be any number that works for at least one inequality. So it can work for the one or the other. In some cases, it can actually work for both. So a graph usually looks like two inequalities pointing in opposite directions. So these ones are most likely going to look like the one we just talked about. That was no solution for the other one. So they're just going to point in the opposite directions. If they do happen to overlap, so this one's going this way, this one's going this way, notice that every single number is covered, so this becomes all real numbers. Because any number you can pick will work for that or inequality. So let's try some examples. Looking here at this first one, I noticed that it's an and inequality, and there are two ways we can do it. We can write it separately as two inequalities, but let's try solving it just the way it is. So 5 is less than or equal to m plus 4, less than 10. So when you solve it like this, make sure that when you do something to one part, you do it to all three parts. So same thing, I'm trying to get m by itself, so I'm going to subtract 4. That means I have to subtract 4 on all parts. So I get 1 is less than m, which is less than, or whoops, forgot an equal to, which is less than 6. Notice that that's the same thing as m is greater than or equal to 1, and m is less than 6. So I'm going to draw my number line. Here's 1, here's 6. M is greater than or equal to 1 is going to be a closed circle, pointing to the right. M is less than 6 is going to be an open circle, pointing to the left. So our solutions are anywhere here in between. So make sure you include that closed circle and the open circle. The way I show that usually on paper is I just shade in between the two of them a little bit more. Let's look at the next one. The next one's an OR inequality. So we have 4c plus 3 is less than or equal to negative 5, or c minus 8 is greater than negative 1. We're going to solve them both individually, so this one I'm going to subtract 3. 4c is less than or equal to negative 8 divided by 4. C is less than or equal to 2, negative 2. And here we're going to add 8. And C is greater than 7. So we have C is less than or equal to negative 2, or C is greater than 7. So I'm going to draw my number line. Here's negative 2. Here's 7. This one's going to be a closed circle pointing left. This one's going to be an open circle pointing right. Since it's an OR, it's okay for it to be pointing opposite directions. All right, next one. We have negative 3 is less than 2k minus 5, which is less than 7. This is an AND inequality. So I'm going to add 5 to all parts. One of the most common things that students do wrong is they don't add it to all parts. And then divide by 2 for everything. And we get 1 is less than k, which is less than 6. Notice that's the same thing as k is greater than 1, and k is less than 6. So here's 1, here's 6. Both are going to be open circles. This one goes to the right, this one goes to the left, so all our answers are here in between. And last example. We have 2p plus 1 is less than negative 7, or 3 minus 2p is less than or equal to negative 1. Solve them each separately, so 2p is less than negative 8. So p is less than negative 4. Go back over here. Negative 2p is less than or equal to negative 4. Divide by negative 2. Remember, when we divide by a negative, we have to flip our inequality. So p is now greater than or equal to positive 2. So here's negative 4, positive 2. This is an open circle going to the left. This is a closed circle going to the right.